Okay, so let's begin the lecture here. And if you remember last time, we left off here on chapter 21, the end of it, where we're talking about, we were comparing these two models. We saw that when we added another parameter to the model, we added this parameter labs to the model, predicting finals. So now we have this homework, exams, and labs. What we saw was that even though r squared went up a bit, and it always goes up or stays the same, it didn't improve the model because adding another parameter cost us a degree of freedom, and we can see that our F statistic went down, and so we didn't have as much significance in the model. And even something else happened is that even though homework had been previously right here significant, it turned not significant. So we said, okay, so that's not helpful to add this third parameter. But now both labs and homework were, both homework and exams, and maybe labs and exams might be another good model. So let's compare them, okay? So this is the next page, and we'll say, okay, so our conclusion from the previous page was we don't want to drop both. Look, the conclusion was we don't want to drop these, even though they became non-significant when we added labs here. We don't want to drop both homework and labs out of the model. We don't. For one thing, we knew that homework was significant before we added labs. And we said this is just because the reason this happened is because homework and labs were very highly correlated. So we don't really can't trust these estimates of the slope right here with very highly correlated variables. So now the question is, maybe we're going to, on the next page, what we're going to do now is we're going to compare these two models, one for predicting the final from the labs. So this is the lab model, labs and exams. This doesn't look very good, does it? Let me see if I can make it look better. Why does it look so bad? It's very small writing, is partially. Let me see if I can get it to look a little better. Okay, so that looks a little better there. So this is what we're doing here. Is going to predict the final exam from these two variables, labs and exams. And here we're going to compare it to homework and exams. So this is our homework model. Both of them include, they have two variables. This is labs and exams, and this is homework and exams. All right, and so now let's look at the statistics here. Let's look at the, now we can look at these r squareds, and we can look, they're all going to be in agreement because we have the same number of parameters. So if r squared goes up, then our F statistic, yeah, that should go up compared to that. We should have more significance for homework versus labs. Yeah, we do. See that? So it's all going in the same direction here because we have the same number of parameters. So we don't have to, so it looks like this homework is the better model. So it says we both have, see, we have three parameters here. 3 parameters. And we have 3 parameters here, too. 3 parameters. So, and our p-value is smaller. So now when there's 3 parameters versus 3 parameters, we're comparing apples to apples. So any one of these statistics is going to give us, you know, if r squared's better, then F will be better, then our significance will be better, and everything. So which r squared is higher? Homework, the homework model. And what is our conclusion? Our conclusion is if you're comparing two models with the same number of parameters, then the higher R squared is going to mean the better model, and it's going to agree with all the other statistics. So what's the conclusion? The homework model's better. Because so when you're comparing two models and they both have the same number of parameters, then higher R squared means higher F, lower, greater significance, lower p-value, all that. So it means better model. Okay? So you can look at any, they'll all be in agreement. There'll be lower standard deviation of the errors. You'll have lower errors here compared to here. All these will be in agreement. I'm sorry, what did I say? Oh, yeah. Means better model. That's what that says. Better model. Okay? So it's simple when you're comparing. It's just when you're adding parameters that R squared is going to go up no matter what or stay the same, so you can't use that anymore. But you should just you should also look at the meaning of the model, what you know about it. Don't you? The homework, if you knew this particular data set, the homework was done every week. The labs were just done, I don't know, monthly or something. They're just not as good a predictor. So now, let's see. So I wanted to show you the relationship between these chi-square tests and these F tests. So here, look at the standard deviation plus above on the right. This one right here. This, and here we could use, here I did a chi-square test on the same data using, on the homework and exams model, and I got this. So what's the relationship between these two? That's what this question's asking. And how is it related? We've always said the standard deviation of the errors, you learned this back in Stat 100, was the square root of 1 minus R squared times the standard deviation of the y's. That's even in a simple regression model, right? So we know that. That's what this is. So the standard deviation of the errors, this one, is equal to the square root of 1 minus, it's the same thing as capital R here. I mean, it's the analogous. Small r and capital R are the same squared in simple regression, and then then in multiple regression, you can only use this capital R. Okay, so that is our relationship. So how does it compare to SD plus errors? Well, that's going to be the same thing, the square root of 1 minus R squared times the standard deviation of y. It's just going to be tweaked by, it's going to be made a little bit bigger. This here, with the standard deviation of y, you just divide by n to find that. So you're going to multiply by that, and then for the standard for this plus, you'd be dividing by n minus p. So it's a little bit bigger. So that's just the relationship. Okay. Any questions? All right. So now we're going to do something fun. I think is more fun. And that is the re-randomization test. So instead of doing these, what are called parametric tests that are based on assumptions about the distributions that the data comes from, and that the errors are the usual assumptions that our linear models depend on, and doing these test depend on? We're going to do something that's distribution free and is very easy to understand. We're going to do simulations, and and we're going to look at randomization simulations, re-randomization simulations. All right, so this is our summary here. I'm jumping ahead because I'm excited about the next chapter. I like the next chapter. But before we do that, let's just review our summary here and just remember what we've done so far. Okay, so in this chapter, what we did was we said that, okay, that we're going to be using T and Z tests on those individual slopes in the multiple regression after we do these F or chi-square tests for the overall. That's what we did. And these T and Z tests are the same thing we did in the simple regression, but you just have to adjust the degrees of freedom for all the other parameters in the model. And that's, so you have to do that. And it's the same as for the F test. All right, and then you also have to be really careful about interpreting the meaning of those individual slopes in multiple regression when the predictor variables are very correlated. Sometimes they don't make sense if you have this multicollinearity. All right. And then this other idea that we looked at was that whenever you add a parameter to a model, you do increase the R squared or keep it the same. But this doesn't mean the model has better predictive value. All right? Because it costs you another degree of freedom. So that's basically each time you add a parameter, it costs you a degree of freedom. So you have to look at the F statistic or other things besides the R squared when you're adding parameters. All right, now for the re-randomization test. I like this one. All right. So, all right. So, the T, the Z, the F, and the chi-square tests, all those tests depended on the assumptions that the errors in our linear regression model are independent, identically distributed with normal distribution, mean 0, and they have the same variability, sigma squared, across all the x's. All right, now, this randomization test is, or re-randomization test, is a non-parametric test. It doesn't depend on what the distributions that our data comes from. And it doesn't depend on these assumptions. It has the advantage of just being a distribution-free, very easy way to understand what we're doing as well. So what we're going to do is, remember what the null hypothesis is. The null hypothesis is always that what we see is just due to random chance, right? So in this case, we were assuming that these 107 scores, these 107 students and their scores, they were randomly sampled from a much larger population of like 2,000 or 3,000 or something Stat 100 students. So we're just assuming that. That's not even really what happened. I mean, usually it's not what happened. You make these assumptions about some ideal larger population, sometimes an infinite population, usually, and you're just thinking, okay, whatever you see is somehow randomly sampled from that population. But there's another way to imagine that randomization. Remember, all significance tests depend on randomization because what the null model says that what you see is just there by random chance. So you have to envision you have to make sure that whatever your situation is, that it can translate into some model that's just due to random chance. So we can use the computer to simulate a very nice random process, and that's what we're going to be doing with these randomization tests. The idea is, let's just look at simple regression, okay? So for example, so instead of computing a test statistic, by estimating those standard errors, assuming these theoretical underlying normal distributions or large enough samples that the central limit theorem kicks in, and assuming that we're randomly sampling from a larger population, we do computer simulations to produce randomization distributions. Okay, so this is what I mean. So in our example, we found that we had a correlation coefficient of this, 0.3926 between homework and finals in our sample of 107 students' scores, and we were assuming they were coming from a larger population. And we got this regression equation, okay? And we have this null hypothesis that the final scores are not linear related to the homework scores, that they're in the whole population of thousands of students, there's no correlation between how well they do on their homework and how well they do on the final. That's the assumption. And then the alternative is, that there is some correlation. That's why we see this big an R as this in our sample, because it reflects a real correlation in the population. All right, so that's the idea. So now another way you can envision this is you can say among these 107 students, if there really is no relationship between what their homework score is and what they get on the final, then we could expect to see any of the 107 final scores randomly associated with any of the 107 homework scores. In other words, we could scramble up the 107 final scores and randomly assign them. Okay? So here's what I mean. Let's just look at 20 of them, the first 20 of them, okay? So imagine, so these are what they actually got. So student 1, observation 1, didn't do very well. 30.47 on the homework and a 52 on the final, okay? This student got a 90. Oh, there's a terrible, look at this, 93 on the homework, but got a 46 on the final. Boy, these are real scores too. Here's an 88 on the homework, 72. They didn't do that well on the final in general. But still. Okay, so this is the actual. And this is where we got that correlation from. Now, imagine putting all these final scores inside a box and then randomly scrambling them up, shaking the box, and then randomly choosing one and assigning it to student 1. So pretend they were on a box. I'm just going to close my eyes. Okay, whatever I got there, 72. Okay? Pretend it was just a random draw. I'll assign that final to this person. It's better than that one. Okay, I assigned it to this one. Then I'll do it again. I'll pick the next ticket out of the box, whatever it is. Let's say it was 76. And then I would assign it to the next student, and so on, and so on, and so on. All right? Then what I'd do, so now we have these scrambled finals, right? And their actual homework scores. And then we compute an R. What's the correlation coefficient between them? Remember, the null says that the correlation coefficient is 0. The null says that what we got is as if it has no that it's just by random luck that we got this. That the real distribution is has a correlation of 0. Okay? So, so we do that over and over and over and over. Okay? And let's say we did that 1,000 times. We'd have 1,000 R's, each computed from 107 homeworks and scrambled finals. And then we could make a histogram of those. We could see the distribution of the R's based on the null, that there's really no correlation between the two. So basically what you would have here is, so these are the, okay, so here, let me just show you. So these are the actual homeworks that these people got. And here is the actual finals. And we're saying that the correlation between these two sets of numbers, the null says that this is just due, that there really isn't a correlation. We just happen to sample these students just by the luck of the draw. That the null is that you're not going to get a correlation of 0 every time, and we got that's small enough it's just due to chance, we'll say, okay, let's just do it. If it really was due to chance, let's see how likely it would be to get that high an R if we scrambled the finals. So these are just random. It's assuming this came from random. So here, let's do it. This is one random realization. And what we're going to do with this random realization is we're going to look at these actual homeworks and the random ones. These are random pairs. And we're going to compute an R from them. And then we're going to do it over and over and over and over again, so we'll have 1,000 R's. And then we'll look at the distribution of those R's. It's the absolute value of R. So we're saying you can't get a negative. If you got a negative correlation, we're just going to take the absolute value. That's why capital R. Okay? And we're going to compare it to, we're going to compare this one, see how likely, is this just a typical one that you'd get from that, or is this really beyond what you'd get? Is it very unusual? So these are the random ones, and we're going to look at this one right here, and that's our actual R squared. These are that's the random pairs, and these are the actual pairs, or you could say our observed sample pairs. That's what the usual language calls them. Observed sample pair, actual pair, from the observed sample, and we get an observed sample R, which is equal to 0.3926. That's what we had before. That's this. And we're just going to place that on the distribution and compute a p-value that way. Okay? Does that make sense? So what we're really doing is what we're always doing. We're just doing a hypothesis test. We're testing, what are we testing? If our observed sample R that we got equal to 0.3926 is beyond what we'd expect, is well beyond, more extreme, is much different, I'll just say, is much different than the R's you get, the R's we get from random scrambling of the homework and the exams. That's all we're doing. So we're creating our own, instead of our own distribution of the R's, instead of relying on all these assumptions that we have to rely on, and creating a test statistic that we look at, like we do with the F test and the Z, all those tests. So that's all we're doing. So let's see what happens. We can do it with the computer. Yeah, why don't we do it? So here's the histogram, and we'll do it. We're going to get a different thing each time, but this is what I got when I did it. And I said, here's a histogram of the 1,000 such R's. See why they're always positive? Because this is going to be this is the absolute value. R is the absolute value, so it's always greater than or equal to 0. Okay, so if it was negative, we just took the X. That's why it looks like this. And our sample is right here. This is our sample. See where it fell? It fell right at almost to 0.4. That's almost to 0.4. That's the sample. That's our sample R. The R we really got in our sample, not through the randomizations. And the question is, how does this compare to the 1,000 other R's? And you can see not one of them was as extreme as that, and that's why we got a p-value of 0. That's what we're asking. That's what all hypothesis tests ask, but this one we actually enact. This is a hypothesis test, just like all of them. But this is saying the null is that, hey, if this was really, if R was really 0 in the population, wouldn't you think that when we do it 1,000 times, we'd get an R that big just by luck? And we didn't. So we would reject the null. So that's all we're doing with every significance test. You're looking at how your test statistic, in this case, it's very clear to see how your test statistic compares to what you'd get just by random chance. And this p-value right here is how likely it is. And so far, it's 0. So let's do it on the computer, and we'll see what happens. Because here, if you just want to look at the next part of it, and then we'll do it, it says, here's the histogram after 100,000 R's were computed. Note that the p-value, so here we have the same exact, R. It's just this R right here. It's the same thing. It's still our sample R. And now, somehow, it went up a little bit. That's because after 100,000 times, we did happen to get, just by luck, a few R's as big or bigger than that, just by the luck of the draw. Okay? Does that make sense? All right. So let's enact this, and you'll see. And by the way, it compares, these p-values are pretty similar to what we got when we did the actual test. We got very small p-value. But let's go to our computer, and here you can do this yourself. So here you can just go to, first of all, you can see what the scatter plot looks like. We're predicting, from homework, we're predicting final. And we're wondering whether, you can see the regression, and here's our R. And the question is whether this could have come, if you just look at it without the R here, without the regression line, you're wondering whether this could just come from a random, or, if there really was no correlation at all in the population, whether you'd pick 107 points with that strong a correlation. It doesn't look like it would be that unusual, right? Does it? I mean, there's a lot of random scatter. But then when we do the re-randomization, so let's just go to that. So we'll pick the same variable here. This is final and homework. And we get the same R here. Okay? That's chi-square. We could do an F. We'll get the same R. And that's our p-value. All right, now let's do it by re-randomization. Oh, after 1,000 re-randomizations, we didn't get anything. Okay, let's see what that looks like. So there's our re-randomization. So that's amazing, isn't it, that that computer did it that fast, actually did the randomizations that quickly, and computed an R for each one of the 1,000. This was not possible when I was learning statistics. I mean, we always said, oh, in the future, long in the future, sometime you're going to be able to, if we could only do this, we wouldn't have to do statistics. It would revolutionize everything, and you wouldn't have to learn statistics the same way. But really, we haven't changed the way we learn statistics that much, but it's changing. I mean, computer simulations are becoming extremely important, and they tell you so much. So you guys are so lucky to be able to learn statistics now using this and really be able to visualize it compared to, and this is just like futuristic when I was learning it. Oh, someday you'll have computer power, you could do this. And I never imagined I could just do it so quickly. I thought it would take a long time. So, sort of amazing. Okay, so far we didn't get anything, but let's try it more times. So each time I click on this re-randomization, watch. This is going to go up by 1,000, and watch this to see if we get, just by the luck of the draw, one of the R's as big as our sample R. So you can see now it went up to 2, 3, 4, 5, 6. Whoop, there it did. So now you can see, it's hard to see, but apparently we did, oh yeah, see? You can see we did just by the luck of the draw, so it is possible to get an R that big, but it's so unlikely, and that's your p-value. That's what it means. Do you think it's cool? I see smiles. Oh my gosh. Some people think it's really cool. I mean, when it comes alive like this, you understand statistics so much better and how cool it is. The idea of random variation and just the idea of just making decisions based on probabilities, informed probabilities, is just extraordinary. I can't think of anything that wouldn't help you make a better decision about, and it's really amazing. And just to understand it at such a gut level this is why I love these simulations, and because you can just get you can trust them. You understand what's going on. So we can do it a few more times, and let's see what happens. We keep doing it. We can do 100,000. Whoops, see, it went down because we've done so many. But you see? And look how smooth the curve gets. See how beautiful? It's jagged. More times you do it, it gets smoother, right? It's so nice. I just want to do a few more. You'll see how it gets really pretty and smooth. I just think it's beautiful. Okay, I'm going to go up to 100, just like I did before. And you can see how pretty it looks. So you can really get a feel that this is pretty much beyond a reasonable doubt. We've got strong, 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 strong evidence that ours did not come, even though it could happen, and it did. We think there's some correlation there. That's the idea. And guess what? We can do it also with, okay, well, let's go back to the notebook. And we're going to do it with multiple regression too, with 2 predictors. So let's just write down so you don't forget what we're talking about here. So this p-value, and p-values always mean this, p-values measure the probability that are observed, what we saw in our sample, the actual sample R, could have come from the random scrambled, from the randomizations, from random scrambling. And that's always the null. You assume, that says from random scrambling, our null hypothesis, you assume the null, and you say, okay, what's the likelihood you'd see such a big test statistic, such a big R, or more extreme, if that was true? So in this case, P is essentially 0%, so we reject the null, that it could have been come from random sampling, that it could have, come from random scrambling, not sampling. What I mean from from taking a random sample from a population that had no correlation. And here, the null is that it just comes from this random scrambling, which is essentially the same thing. Okay? So you reject the null because it's almost impossible, because we see that it's almost impossible. It's not impossible, but it's almost impossible that we'd get such an extreme, or even more extreme, that's what it's measuring, everything to the right of it, such an extreme R under the null. You know, but you can see it's almost impossible, but you know, when we really looked at it, when we looked at that scatter plot, you probably wouldn't have thought that it was so impossible because it didn't look, the points didn't fall in a line. So our intuition is really weak about this. What I mean is this. When you go back here to this, at least for me, my intuition's weak. When we go back here to this scatter plot, homework and final, does that look like almost impossible to have gotten that if there was, you know, from a population that just was random scatter? Does it look so unlikely to people? I mean, would you just think, oh, that's just only happens one in... It just, I mean, certainly if it was probably this one looks more, I mean, if it was like this, then I'd know it was impossible, right? But, you know, I mean, that doesn't... How about that one? Do you think that one is just as impossible almost? Okay, so that's the idea. And then on the next page, we're going to do the same thing. So what are we going to do now? We might as well, since we're here, do it. All right, so here's the final, and let's do homework and exams. All right, let's just first do the chi-square test. Look at that huge R. And here's the F. Look at that huge R. It's very, very tiny probability that it would happen. And now we could do the re-randomization. All right? So how likely is it going to be to get that big an R? Well, let's see. This is after 2,000. We haven't gotten any. It's well beyond what you'd get by randomization. Let's try some more. See if we get, watch this, see if it changes. I don't think we're going to get one that will show up because we're so far beyond. Look at this. We're not even close. Yeah, it's not going to show up. Look how the homework, the p-value keeps staying at 0. For the exams, excuse me, for the exams. The homework isn't as significant as the exams. It keeps changing but, okay, so that's what we're going to do on the next page. So let's go to the next page and see what we're doing here. Okay, so we're going to add another variable. And we found that R is equal to this 0.6198. All right, and here's our model. And the null is that both slopes equal 0, that there's no correlation, multiple correlation in the population between what we'd predict, what we can predict from homework and exams, and the actual, the predicted finals from homework and exams and the actual ones. All right? So now we can do the same thing to test the overall regression effect. So what are we going to do? Same thing. We'll put these actual finals. So these are the actual ones, right? And so this student got a 30 on the homework, a 60 on the exams, and a 52, et cetera, et cetera. And so now these are the actual and the actual. And now what we're going to do is imagine putting all these finals inside a box, shaking it up, and then closing our eyes like shaking up and just pulling one out. Okay, so we're assigning 64 to this student. We're keeping his actual homework and exams, keeping those. Now we're assigning that to him instead of this one. And we do it again. Let's say that was 46, etc. All the way through, and we get this whole scrambled finals here. So now what we're doing, so these right here, these are the actual homework and exams for each of the students. And these are the scrambled finals. So what we're going to do is we're going to compute R between these and these random ones. So what will we have here? We'll have an x1 that's actual, an x2 that's actual, and then we'll have a random R, y, a random y. Okay, so that will be what we have. And we want to know how well these two predict the random y, as opposed to here, where these are all the actual ones. Here we have the actual, we have the x1, the x2, and then we have the actual y. All right? And this led to an R equal to what? 0.6198. And this one is from this, the data set of the random ones, you know, let's say blah, 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 all the way down to some random one, let's say it was 70. These random ones, we're going to take for each, we're going to look at that data set, and from this one, we'll compute an R for each randomization. Okay? So we'd have 1,000, we'll do it 1,000 times, and each computed from the 107 real homework and exam scores. We keep those paired up, right? Because we just want to see how well those would predict some scrambled final, because that's the null. The null is that our model, this model in predicting final, does no better than random chance. You might as well just predict the average of all 107 finals, which is what you'd do if it was just under randomization. And then we make the histogram, and it's the same thing. Okay? So that's the re-randomization test. Let's just look at this again. So this right here this is our observed right here. Okay. And it's just like, well, look at this p-value here. It's obviously too extreme to fit a random scrambled model. And you can see that it's, you know, this shows that it's too extreme. It's so far out. This is so far beyond the other R's that our p-value, p is equal to 0%. Too extreme a value to fit, too extreme a value to fit the random model, the null. Okay? And even when we do it more times, we get the same thing. This is the same thing. Okay? So we reject the null. Any questions on that? All right. Yes. Yeah, his question was, is the p-value the percentage of r's that either equal or went beyond the r observed one? And yes, the answer is yes. That's what a p-value is. And usually, when we do our usual z-tests or t-tests or chi-squared or f, we're just, instead of having this empirical, see, this is what this is the empirical sampling distribution of R under the null after 1,000 randomizations. And this is an empirical. What we're doing, we're using an empirical sampling distribution created by computer simulations. So we can visualize it and see it. What we're doing with the other tests, all the other tests, when we do any hypothesis test, is we're using an idealized sampling. We're not using an empirical sampling distribution. We're using one based on theory. Does that make sense? And based on certain assumptions. Here we're simulating it. I should have said that for all of them. That's what this is. Instead of a sampling distribution based on, assumptions about what we know about distributions in a sort of idealized one, it's an empirical one. Based on experimentation and simulations. It's easy to do. It's so much fun. Okay? All right, so that's that. And now, what are we going to do? Okay, now we're going to do something called ANOVA. Well, you're probably thinking, ANOVA, analysis of variance, haven't we been doing ANOVA all along? That's the whole, ever since we started regression, we've been doing analysis of variance, breaking up the total variability of the y's into the signal and the noise. So why are we all of a sudden calling this ANOVA? And it's going to be ANOVA for comparing group means. So maybe I should, so it's basic, so why are we calling it something different? It's kind of confusing. Let's skip to just the summary at the end of this whole ANOVA. Let me see where it is. There's, Okay, maybe on page 131, before we even start, so you don't get confused. So on page 131, the summary at the end of this whole section called ANOVA, the term ANOVA is confusing because it refers to two things. It refers to this situation that we're looking at, comparing group means. When people say ANOVA, that's usually what they mean. But it also refers to analysis of variance as the procedure of partitioning the total variation of the y's into two parts, the sum of squares due to the model and the sum of squares due to the error, to assess the fit of a model. This procedure is done both for comparing means and regression. In fact, I'll show you if we have time, that this comparing means is just a special case of regression. That's all it is. It's a special case of regression where in fact, I'll definitely show you because it's important. What we're going to be doing here is a special case of regression predicting a quantitative y variable, but instead of having quantitative x's or a mixture of quantitative x's and categorical x's, we have solely categorical x's. So each x has and that's all we're doing here. We'll talk about that later. First, let's just read along here. Okay, so back in Stat 100, we tested hypotheses comparing the averages of two populations using the two-sample z-test or the two-sample z-test. We said the observed difference, like between male and female exam scores, minus the expected under the null of 0, that there's no difference, divided by, and this is the way we combined the standard errors from, let's say, the boys and the girls. Okay? We took the square root of the sum of their squared standard errors. So we just did a z-test like that for the standard error, the difference, with the null being that the difference was 0. Or else we could have done a t-test by slightly tweaking the standard errors. So that's what we did. Whoa, 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 whoa. All right, but often we want to compare 3 or more group means. Like, let's say males, females, and let's say there were enough other besides males and females, like transgendered, that we could do that. In our class, there isn't enough, but let's say there were, then we'd have 3 groups, and 3 groups, it's the same old story, 3 slopes, 3 groups. You can't just boil the differences down to a single signed number. So what do? We square the differences and sum them, giving us a test stat that's the ratio. When you sum squared differences, it's the ratio of 2 variances. This is just what we did for multiple regression, where we had to assess whether more than 2 slopes, whether a whole collection of slopes were significant, and couldn't boil it down to a single number. It's the same thing, and we can do a regression. You'll see it's exactly the same thing. It's easier, much easier. It's a special easy case of what we've been doing all along. So, as we did in regression, we'll use ANOVA and the f-stat, or the chi-square stat, for large samples. And the idea is we break the variance into 2 pieces. You have the sum of squares, total variation of how far the y's are, whatever you're trying to predict, how spread out they are. Look, if they were all exactly the same, there'd be nothing to predict, right? And then you break it into a model and errors. So in regression, what did we do? We broke it into sum of squares total was equal to the variation predicted by the regression line. So that was SSM, or R, which was R squared times SST, plus, that's the sum of squares, how much the model improved how much of the variation is explained by the model, the regression line, and then how much is left in the scatter around the errors, the scatter around the regression line. And that was 1 minus R squared times SST. So now in comparing averages, what does this mean? So now what do we have? Let's say we're trying to compare exam scores for 3 groups. Let's say in this class it looks like Asians, whites, and other. Okay, 3 groups. And what we would be doing, so this would be a case where you're predicting a quantitative Y, final exam scores, based solely on group membership, on this categorical variable, whether you're Asian or not, white or not, or other or not. Let's say others, because that's what it looks like. All right, so here, so what would we say? We'd say the sum of squares total, that's the variation around the final exam scores, could be predicted by what? If we're basing it solely on group membership, then it's just going to be based on the average final for each group. The group means, right? It's our only, if it's just a variable, this factor variable, groups, where you can have white or not, other or not, Asian or not, etc. Okay, so it would just be the group means, that would be our model, plus what would be the error? The error, the spread around the group mean. All whites are not going to score the same final. There's going to be a lot of spread around them. Same with every group. So it's the sum of squares within each group. And it's the same idea. All right. So it yields this same test statistic. And now it's done exactly the same way. And so this is your mean square model. This is based on the group means over how much variation there is within the group. Look, if everyone who was white got exactly the same final exam score, there'd be not, then you could easily, you could predict, hey, you're white, you get that. But obviously, there's a lot of error around the group mean. that's the error. So it's signal to noise. And now what do you divide by? Well, the number of parameters are just the number of groups, because each group would have a group mean that you'd make a prediction from. And so it's just P minus 1 is G minus 1, number of groups minus 1, and N minus the number of parameters. Each group would be a parameter, whether you're in that group or not. And then we just do exactly the same thing. So it's a much easier case, a very simple case, extremely simple case of regression. Think of it as making predictions just based on group membership, also known as stereotyping. Right? We do it all the time, but now in statistics, we're just going to look at how valid that is in certain cases, or what it tells us. Okay. It's just making a quantitative prediction based on stereotyping, based on group membership. Yeah? What does what represent? I'm sorry, I'm kind of deaf. I didn't hear your question. SSW represents the variation around the errors. You're Asian, right? So if I said, let's say the Asians got a 80, that was the average. But you're going to have some error around that. Not every Asian is going to score 80, right? So that's the error around the group average for Asians. So let's say you scored an 87, you'd have an error of 7. Does that make sense? Okay. So it's just, and the bigger that error is, the harder it's going to make a prediction, right? Because people vary within each group. Okay, so that's all that is. That was the question. What is this? This corresponds to the error. And you're going to break it up the same way, r squared and 1 minus r squared. Everything's exactly the same. In fact, we can do the same pictures and everything. So let's do an example, and you'll see what I mean. So you're going to think this is easy, this stuff. All right. So two experiments were done to compare the effect of 3 drugs. In each experiment, 3 subjects were randomly assigned to each of the 3 drugs. So the null is always that the 3 drugs have the same mean. We should write it in more formal language. So the H naught is that in the population, which is the group mean in the population, mu, for group A is going to be equal to mu for group B, which is going to be equal to mu for group C. So what is mu measuring? It's measuring the effect, some response, some quantitative. We're measuring some quantitative response. Okay, so this axis is a measure of some quantitative response to this drug. And this has no meaning. This is just group A. The x-axis has no meaning. It's just I just put them next to each other. These are almost like little box plots or something. So this is group A, group B, and group C. All right? So we have experiment 1 and experiment 2. And we're trying to see, the null is that, look, what are these group means? A, B, and C. Here, for this experiment, the average response of these 3 people to the drug was 1. All right? And for group B, that was another drug. And the average response between the 3 people who took group B was 2. I just made a super easy example. So we have this. We're comparing whether drug A, which yields 1, drug B yields 2, and drug C yields -3. Okay? So that's one experiment. And this is just some quantitative response. Okay? And this grand mean says, what is this? This is the average of all the subjects. So if you said 0.5 plus 1 plus 1.5 plus 2, took all 9 and took their average, divided by 9, you got 0. I just made it simple. All right? So these 2 groups are above average on some measure, and this one's well below average. That happened in our first experiment. Now our second experiment used the same drugs, drug A, drug B, and drug C, let's say. Let's just pretend. And here, the average is 1 for a group. It's exactly the same. Just looks different, but it's exactly the same. I made them so they have the same averages, 2 and -3. All right, so now the question is, so these are 2 experiments, and when we compare 1, 2, and -3, they're placed differently on here, but that's really, they're the same numbers. So if we just look at 1, 2, and -3, just looked at the averages, 1, 2, and -3, they look like they were the same. Each experiment would give us the same evidence, right? But we have something called within group variation, right? Let's say all 3 people got exactly 1, and all 3 people got exactly 2, and all 3 people got exactly -3, then wouldn't that be more evidence that these drugs are different than if there's like a big spread? Like here, there's a big spread. Like even in group A, one person got high as a 6, another -4. See, there's an overlap. So here's the mean is 2, here -3. There's an overlap. There's a big spread. Here, everybody in group C is different than these 2 groups. So why don't we do an eye clicker? We haven't done one yet. And I want to say, in which experiment does it look like there's stronger evidence to reject the null? That will be your eye clicker question. It's pretty easy. Okay. Well, I better hurry. I can't do this. I'm going to have to go through examples because it's getting late. All right, did everybody pick one of these? I'll just give you a few more seconds and stop it. Okay, pick one, anyone. These are only eye clickers, so just, please, just choose anything if you haven't done anything yet. Okay? All right, I'm going to stop it, and let's see what you got. Experiment 1 has stronger evidence. That's good. I'm glad you said that. That's the right answer. So let's look at that, and okay, because in experiment 1, group C is clearly different. Experiment 1 has much smaller within-group spread, so it's more reliable evidence. So let's write that down. All right. Basically what this is, okay, so this is experiment 1. And look at the spread between the group means. How do the 2 experiments compare? Even though they're graphed differently, they have the same exact mean. So the spread between them means how far 1 is from 0, 2 is from the overall average here. And they're the same. They're the same because the means are the same. You're just looking at the means. They're the same because both experiments have the same means. So they're between, so SSB, the sum of squares between, are going to be the same. I'll explain what that is on the next page. But look at this spread within each group. This has a tiny little spread within each group, and this has big spreads. Experiment 1 has smaller within groups spread. So that's why it has more evidence. Those of you who saw that chose that for that reason. All right, so why don't you read this on your own here. Hello, everyone. So let's turn, this is page 115, the chapter 23 summary. So in chapter 23, we're looking at comparing group means called ANOVA, and let's compare it to regression that we've done before. And we see that the statistic, the F statistic, looks very similar. We're comparing basically the signal to noise, the model, the strength of the model to the strength of the errors. And what jumps out as different probably is this, here it's the degrees of freedom for the model is the number of parameters -1, and for the errors it's n, your sample size, minus the number of parameters. Well, here for ANOVA, G, the number of groups, is the number of parameters. In fact, this ANOVA is really a special case of regression. And we can see this, we could see this because we could write it as a regression equation. Let's see, we can change, let's change ANOVA, we can change the example we did on the previous page, which was the example of the experiment. We're comparing 3 different types of drugs, drug A, drug B, and drug C, on some quantitative response variable. Let's call it Y. Well, we can change the example on page 114 to a regression equation. And we can do this for any comparison of means. So what we have is we had, in the previous example, we had a quantitative Y variable. It was a drug response, a measure of how well these 3 different drugs worked. And there were drug A, drug B, and drug C. And we can say, okay, remember the null hypothesis was that in some wider population, the mean response for drugs A, B, and C was all the same. And then what we're trying to see, the alternative, was they're not all the same. So the model we were creating is that we can predict the response variable, the response to the drugs, based on group membership, right? So what we can do is we can change that group membership into 3 binary variables, like group A, and you'll have, so our predicted response, Y, is equal to some slope times group A, plus some slope times group B, plus some slope times group C, where these are each binary variables. So what would this be? It would be 0 if in A, if in group A, excuse me, 1 if in group A, obviously, and 0 if not. And here it's going to be the same. So there'll be 3 binary variables here. So this would be 1 if in group B, and 0 if not. And this would be 1 if in C, 0 if not. Okay, so how are we going to, what's this model going to look like here? Well, we're going to say, okay, what will be our best prediction for this response if they're in group A? So if they're in group A, they'd have a 1 for group A, and the slope here would just be the mean, the population mean for group A, all the Y's. And here, it would be, if you're in group B, it would be 1 for this, and 0 for these 2, because if you're in group B, you're not in A and C. So now, if you're in group B, the best prediction for the Y is just the mean of all the Y variables for group B, the mean of all the Y values. So that would be the mean for B, and this would be the mean for C. So what this model does is just says our best prediction for our Y depends on the group membership, and we're predicting the means for each group. That's all that's saying. So what we're doing here, so this is basically our regression equation. And so why is the number of parameters equal to the number of groups? Because we're making estimates for 3 parameters here. An alternative way of writing this that people see all the time is we could also choose one of these groups as sort of our baseline comparison group and call it the intercept. So you could write it, can also be written, or actually even more often is written, as you're making this prediction for Y, and then let's say we set group A as our baseline that we're going to compare these two groups to. So that would be the intercept. So we'd say that would be our intercept, right? And we'd put in here, we'd put in the mean for group A. And then we'd say, we just have that, and then we'd have two. Again, we'd have a slope for group B, 0, 1 again, and a slope for group C. So these variables are 0, 1 variables. So if you're in group A, then this is 0 and this is 0. So it predicts the mean of A for A. So if you're in group B, what's it going to predict? This is just going to be compared to this. So if you're in group B, this still stays here. There's no variable here. This turns to 0. So what's this going to be? This is going to be the mean of B, group B, minus the mean of A. Then those two things would cancel out, and we'd get just what we'd want. And so this would also be, for this, the slope for group C. When you're in group C, that's 0. So now, the best prediction for somebody who's in group C is the mean of C. So that would be the mean of C minus group A. So just subtract off the intercept. And that makes, it's useful to do this. This is not always, this could be any of the groups. Say for example, group A. That could be any of the 3 groups. Usually you'd pick one baseline that you wanted to compare the others to. Okay? So why is this useful to do, this form? This form is useful if you're interested in comparing these 2 groups to a third one. If you're interested in saying, how do the 2 groups differ from the other one? They're essentially the same thing. If you're interested in setting one of the groups as a baseline. Okay, so that's the idea. And that makes perfect sense why the number of groups is the number of parameters and it's just a linear model. So basically, let's look at an example now on the next page. All right. So we've got. Okay, so let's turn the page and we're on chapter 24 and page 117. So what does this sum of squares total, sum of squares between, and sum of squares within mean in the context of this example? First of all, what does it mean in general? So this sum of squares t is just our usual sum of squares total, which is just the variation around the y's. So if there was no variation of all these y variables, all these y values were the same, there'd be nothing to predict, right? So it's just how spread out they are. So this is taking each of the 9 in our example here, each of these 9 responses, to the 3 different drugs, color-coded here as red, blue, and green, and we're subtracting it from their overall mean, which is 0. So if you add all these 9 numbers up, divide by 9, you'll get 0, the grand mean. So we're just taking the distance from each of them and squaring them. And we're saying that it's our usual. This is equal to what our predictions, which is the group means, so 2, 1, and -3, each subtracted from the overall, right? So this is how much better, you see, the null hypothesis is just you're going to predict the group membership means nothing. That whether you took A, B, or C, whichever drug you took, it has the same mean. It does the same thing. All the means are the same. It's the null hypothesis, so they're all equivalent to the overall mean. So the mean of all 9 of them, 0. And what this is saying how much better the model does compared to that. Our model is saying let's predict for everybody who took group A. Let's predict the mean for group A. For everybody who took group this is switched here, sorry. This is group A, and this is group B. For everybody who took group B, it's the mean for group B, and for everybody who took group C, it's the mean for group C. All right, so, and then, what is this? This is our error. So we're comparing, basically, the strength of the model to the strength of the error. And what's the error? That's the spread, the variation within each group. So all these groups, they're pretty close together. There's not much error if we predict the group means. Imagine if all 3 people who took group B got a response of 2. All 3 people who took group A got a response of 1, and all 3 people who took group C got a response of -3. Then you would know the model. We wouldn't need a significance test to tell us that the model was doing something. But, so we're comparing, basically, so we're breaking down the overall variation in the response into a part that's due to the signal and the noise, like we always do. So it's very easy to calculate these with only 9 points, so let's do that. Maybe we'll get you a better feel for it. So what's SST? So SST is just going to be, I'm going to take all 9 points and subtract off 0 from each one of them, right? So let's look at this. So you'd say 1.5 minus 0, 1 minus 0, 0.5 minus 0, etc. Now if we didn't square them, they'd sum to 0, because that's the average right here. If we didn't square them, they'd sum to 0. All right? So we're squaring them. So we say 1.5 minus 0 squared. I'm doing group A first, plus 1 minus 0 squared, plus 0.5 minus 0 squared. And then you could do the same for this is group A. You can do the same for the 3 in group B, and the same for the 3 in group C. So for group C, it would be what? Negative 2.5 minus 3, minus negative 3 squared, plus negative 3 minus negative 3 squared, plus, whoops, what did I do wrong? This is minus 0. Minus 0, duh. Negative 3.5 minus 0 squared. Ta-da. Okay, so we do it for all 9 of them and add them together. And when I did that, I got the sum of squares total is equal to 43.5. You can check. Okay, so this is supposed to be equal to this plus that. And let's see. So now we're going to do the sum of squares between. So what does the sum of squares between mean? It's a strength of the model. So you're looking at our model is predicting these means. 1, 2, and negative 3. So that's 1, 2, and negative 3. Those are our predictions right here. And we're going to subtract off for every single point. We're going to subtract off the overall. grand mean. Okay, so we'll do that. We'll do that. And we'll do that. Now we have to remember, this is for all right here. What we're doing for I equals 1 to 9 for all of these. 1 to n. In this case, it's 1. For all of these, is for all 9 points. We only have 3 here, right? So for each one of these, right, it's going to make a prediction of 2 for each one. For this point, and this point, they'll have the same predicted minus the 0. And then you're going to square them. So there'll be 3 of these, plus 3 of these, plus 3 of these. And if you had 4 points in each, it would be 4, 4, and 4. Okay? So we get what? 3 times 1 squared plus 3 times 2 squared plus 3 times 3 squared. So we do that, and we'll get 42, correct? Is that right? Yeah. Okay, so now let's do the last one, sum of squares with n. And what's that? That's the sum of the squared errors. Your observed minus your predicted. So, for minus the predicted, observed minus predicted. So for group A, let's look what it is. It's just these errors around the predicted. Everybody in group A gets 1 as the predicted value. So this one's 0.5 above, 0.5 above. This value's right at its prediction, and this is 0.5 below. Let's look at the next one. This is 0.5 above, right at its predicted value, and 0.5 below. And same here. So they're same for all of them. We're just measuring the distance each point is from its prediction. All right? So the first one's going to be 1.5 minus 1, which is 0.5 squared. And the next one's right at its prediction, the next point, so that's just going to be 0 squared, 1 minus 1 squared. And this one is 0.5 below, so it's going to be 0.5 minus 1 squared. So all of them are going to follow the same pattern in this example. 0.5 squared plus right? All of them are going to be the same. They have the same distances. So it's going to be the same for all of them.
So this like what's our first one?
So what do we get? We get 0.25 and 0.25. So this is 0.5. This next one's also going to be 0.5. And the next one's also going to be 0.5. Just because it's not always true, but for this problem, we have the same within group spread for each room. So that is 1.5, and we have to check, does 42 plus 1.5 add to 43.5? Yes. All right, so now let's go and fill out the chart. Okay, now we're ready to fill in our table here, this ANOVA table, and it's the usual ANOVA table divided between the model. We're dividing up the total, sum of squares total, into model and error. Okay, so we just computed those. We said the model was 42, the error was 1.5, and they did sum to 43.5. Now what about these degrees of freedom? There are usual degrees of freedom. The degrees of freedom for the model is usually what? It's usually the number of parameters minus 1. So in this case, the number of parameters is the number of groups minus 1. We have 3 groups, so the degrees of freedom is 2. Now for the error, well, it's probably easiest to remember total. That's always n minus 1. So in this case, we have 9 minus 1, which is 8. Now we know this must be 6, and let's check. It's usually n minus p, but p is g here. The number of parameters is the number of groups. So that would be 9n minus 3. And it all checks. So now we're going to look at the mean square. Basically, we're just taking the average. 42 divided by the degrees of freedom, so we get 21 here, right? So we'll say 42 divided by 2 is equal to 21. And then we're going to do the same thing with the errors. So we say 1.5 divided by 6. And 1.5 divided by 6 is equal to 0.25. Right? Now, F is the ratio between the mean square model to the mean square error. So it's just going to be 21 divided by 0.25, which is 84. That's a huge F. Remember, F is centered. The mean of F is 1. So that shows tremendous significance for this model. Now, how would you get r squared from this? Remember that this sum of squares total is broken up into two parts. This is r squared times SST, and this is 1 minus r squared times SST. So r squared must be equal to what? Must be equal to 42 divided by 43.5 is the proportion of the total variance due to the model. So it's extremely high r squared. So, okay, what about this? What's the standard deviation plus of the errors? Well, this is a measure of the sum of this. We have to take the square root of this. This is the mean square error, so we're going to take the square root of that, and that will be the standard deviation plus of our errors. Well, this is easy to do. There we go. And that makes sense because remember all our errors were about 0.5 from their mean on the average. Okay.